Hello everyone, I'm Wang from Oxford. We present point cloud normal estimation network that can focus on relevant neighbor points automatically. As a result, our method is insensitive to neighborhood variance. Let's have a brief intro for normal estimation. The most common way to estimate a normal is through PCA, in which we first define neighborhood range, fit a plane for those neighbor points, and estimate a normal vector from the plane. But how do we know which k performs the best? We have to manually try different k's, plot a curve, and pick the best k from the curve. There are mainly two issues in the PCA method. Firstly, as we show in the last slides, we need to find a k manually. Secondly, it doesn't make sense to use a global k on an entire point cloud because different regions might need different number of neighbors. So, for example, this is a real point cloud in the PCP-net testset. It's obvious that the red patch contains an edge and the blue patch is almost flat. That means it's impossible to define a global k for those two patches. We need an algorithm that can adapt to different geometric properties. We introduce our attention-based network in order to deal with those two issues. Given a point cloud, given a neighborhood that is large enough, for example, set k to 50 when the optimum k is 5, our network can identify which points are relevant to the normal estimation task. Here we visualize attention weights on the patches we showed before. A point with brighter color means it has higher attention weight. In addition to focusing on points that are close to patch center, our network pays extra attention at patch boundaries to identify geometric properties of the patch. This is very similar to what humans do. If we have a patch of points, we would first notice if it contains an edge or contains a corner. Then we decide which points are useful and finally which points are outliers. In this figure, we show 4 attention maps with a different number of neighbors available. Each row in an attention map represents a patch. The leftmost pixel in the row denotes the closest point to the patch center. The attention weights is color-coded using pixel intensity. From the attention map over 5 and 10 neighbors, that is figure A and figure B, we can see that our network assigns higher value to points close to the patch center. This is very similar to the PCA behavior. From attention map over 25 and 50 neighbors, that is figure A and figure D, our network pays extra attention to boundaries. Our explanation is that our network learns to identify geometric structures using the patch boundary. Armed with the attention mechanism, our network performs stably given different number of neighbors. Our network performs better than PCA method as long as more than 3 neighbors are available. We also outperform the previous state-of-the-art with a much smaller model and faster inference time. In order to further control the smoothness of attention, we introduce a temperature parameter that can be learned during training. Attention mechanism has 2 parts. The first part computes a dot product among point features, and the second part applies softmax to get the attention weights. By learning a temperature parameter in a softmax, our network learns to distribute attention weights. So the figure to the right-hand side shows how attention weight changes when using different temperatures. We know that the sum of softmax output is always 1. So if we pay more attention to certain points, other points get much less attention. For example, if our temperature is 0.5, that is the blue line, we focus on 1 or 2 points with very high attention and ignore other points. If we use a higher temperature, we can focus on points with smoother attention weight distribution. We don't know which one is better, whether we should use a sharper or a smoother softmax. So we give the control to the network by learning such a temperature parameter. In this figure, the black line denotes our full model, and the red line denotes our model without learning the temperature. It's obvious that learning a temperature is beneficial to both performance and stability. Lastly, we use a point cloud registration task to show how a downstream application can benefit from the neighborhood-insensitive property. Many downstream applications rely on high-quality normals, such as surface reconstruction, camera tracking, and registration, etc. Given 2 point clouds that are in different poses, ICP can be used to compute rotation and translation between them. Here we show a comparison of ICP convergence speed when we feed normals from different normal estimation methods. In summary, we introduce an attention-based normal estimation network that can identify relevant points automatically. Our network learns a temperature to control the smoothness of attention. As a result, our network performs stably given different number of neighbors and outperform previous learning methods with a much smaller model and faster inference time. We also demonstrate how downstream applications like ICP can benefit from our model. Thanks for your time.